Hello folks, welcome to a mini course on Simple Harmonic Motion. This course will be something like 3 to 4 hours long. There will be something like 12 or 13 videos, each about 15 to 20 minutes long. And by the end of this course, I hope to make you an expert on Simple Harmonic Motion. You will learn the concepts and you will learn the problem solving skills. Now, think of some simple problems. For example, let's say a block of wood is floating in a serene lake. I push it down slightly and release it. It bobs up and down. Is that simple harmonic motion? And if so, what is the frequency? How do I approach a problem like that? Or consider this one, a block attached to a spring which is attached to a wall. A bullet comes and gets embedded in the block and the block starts oscillating. What is the amplitude of the oscillation? What is the phase? I'll come to the phase in a second. Or a block which is already oscillating, someone puts a second block on it which sticks to it, inelastic collision. And together they move. What is the new frequency and what is the new amplitude? What is the meaning of phase and what's the difference between phase and phase constant? Consider two pendula of the same frequency, they are oscillating. One of them at some instant of time is halfway towards its maximum position. The other one is passing through the equilibrium heading towards the minimum. What is the phase difference between the two oscillations? How do you approach, and is there a simple way to solve a problem like that? You will be learning all of these things during this course. You will also learn how to combine rigid body motion with simple harmonic motion. For example, a uniform rod that is oscillating or a rod connected to a sphere that is oscillating. What is the frequency? How about this problem? A hemispherical bowl and a small marble rolls back and forth. Is that simple harmonic? Is there an easy way to find the frequency? Consider problems which combine other topics. For example, electrostatics with simple harmonic motion. You could have a pendulum whose bob is charged and there is an infinite charge sheet nearby. What is the frequency now? Or consider a ring carrying a current I placed in a uniform magnetic field and it is tilted and released. It oscillates back and forth. What is the frequency? So we are going to learn all these problems and more during this course. Now, this is a good time for me to tell you that the prerequisite for this course is you should know differential calculus. You should know derivatives. You will also come across differential equations, but you don't need to know anything about differential equations. I will have a small video explaining to you just what you need in order to continue with simple harmonic motion. Shall we get started? Okay. So we'll get started with what kind of oscillations are simple harmonic and what kinds of periodic motion are not simple harmonic. An obvious one that's not simple harmonic is a ball bouncing up and down. Now that's periodic. There is a time period and there is a frequency. If the collision with the floor is completely elastic, there is no loss of energy, there is no air friction, the ball will bounce forever, always reaching the same height and repeating a certain motion. What is the motion it repeats? If you start at the highest point, it hits the floor and comes back to the highest point and then repeats it. So the time period of the minimum repeating unit is called the time period. So supposing it bounces 5 times a second, quite a high frequency. If it bounces 5 times a second, then each bounce, that is each oscillation, takes 1/5 of a second. So the time period is 1 over the frequency. So this is a periodic phenomenon with a time period and a frequency, but it is not simple harmonic. Let's look at a second example. A pendulum. Now this pendulum is oscillating with a large amplitude. This is not simple harmonic. We will see that when the amplitude is small, that is, it makes a small angle with the vertical, then it is described beautifully by the simple harmonic equation. We'll come to that. But right now, you can see that the pendulum has a time period. If I start at one extreme, the time for it to go to the other extreme and come back, that is the time period. That is one oscillation, because that's the motion that keeps repeating itself. Now, let's say it makes 10 oscillations per second. So each oscillation takes 1/10 of a second. Again, frequency is 1 over the time period. Consider this other example, a wire held tight under high tension between two rigid walls. And right at the center, attached to the wire, is a bead of mass m. I pluck the bead. It oscillates. If you don't mind sound effects from me. Now, question is, what is the frequency of that oscillation? Is it simple harmonic? Again, we will find that if the amplitude is small, it is simple harmonic, and it's very easy to find the frequency. From here, we learn to find frequencies of much more complicated systems. So let's start with the prototypical example of a simple harmonic motion, and from there we will see what can be considered simple harmonic. So we start with a block attached to an ideal spring whose other end is attached to a wall. There is no friction on the floor or in the air. There's no air friction. So if I disturb the block, it will oscillate forever. Now, first thing, let's understand the ideal spring. An ideal spring exerts a force proportional to the amount by which it is stretched or compressed. Check out this block and spring system. Right now the block is in equilibrium. So we start with an equilibrium position. Equilibrium is when the net force on it is 0. Now the spring is not exerting any forces on it because it is neither stretched nor compressed. Now let's see what happens if I move the block to the right. When I move the block to the right, the spring gets extended, so it pulls back. So the spring exerts a force trying to pull the block back towards equilibrium. That's called a restoring force. Now the restoring force doesn't really restore equilibrium because if I release it, it keeps oscillating. Okay, let's see what happens if I push the block to the left. When I push the block to the left, the spring gets compressed, and once again the compressed spring pushing the block to the right exerts a force again towards equilibrium. So you have an equilibrium position, and if you push it to the right, there is a force pulling it back towards equilibrium. And if I move it to the left, there is a force pushing it back towards equilibrium. This is called a stable equilibrium. Now, a stable equilibrium is the first prerequisite for an oscillation. Now, if I move it to the right or to the left and release it, it oscillates. Why does it oscillate? It oscillates because, starting here, there is a force pulling it back towards equilibrium. So as it moves towards the equilibrium position, it picks up speed faster, faster, faster. By the time it gets to the equilibrium position where the force is 0, it has already got sufficient speed that it overshoots the equilibrium. Now there is a force acting in the opposite direction to the velocity, which slows it down, brings it to a stop. But by the time it comes to a stop, the spring is highly compressed. And what does the spring do? Pushes it back towards equilibrium. So once again it picks up speed, and once again it overshoots the equilibrium, and this way it keeps oscillating forever. So what are the prerequisites for oscillation? First, an equilibrium position. Second, it should be a stable equilibrium position. Now, is that enough to produce simple harmonic motion? No. You need one important condition, which is the so-called restoring force should be proportional to the displacement. Let's check it out. I have set up a coordinate system here. The spring has a spring constant 2 newtons per centimeter. That's the same as 200 newtons per meter. When we start doing calculations, we'll be using 200 newtons per meter because we'll be using SI units, meters, kilograms, seconds. And for force, newtons. Now this spring obeys Hooke's law. What does that mean? That means if I move the block to the left or to the right, the restoring force is proportional to the displacement from equilibrium. Okay? Now I have marked the x-axis so that each marking is 4 centimeters apart. So starting from equilibrium, let me move it 4 centimeters to the right. There is a force to the left of 8 newtons, and we have written it down as -8 because the force points in the negative direction. When I move the block so that the displacement is 8 centimeters, the force is k times x, 2 times 8, 16 newtons, and the minus sign tells me the force points in the negative x direction. Remember, x is measured positive to the right. And lastly, when I move it to 16 centimeters, the force is minus 32. Let's start compressing the spring now. When I move it to a position of minus 4 centimeters, when x is minus 4, the force is plus 8. When x is equal to minus 16, the force is plus 32. You are beginning to see now that the force is given by minus kx. That is, when x is positive, the force is negative. When x is negative, the force is positive. So the force has the opposite sign as x, and it's proportional to x, and the proportionality constant is k, and that's called the spring constant. So what is the condition for simple harmonic motion? In the case of linear simple harmonic motion, later on we'll come to rotatory simple harmonic motion. Right now, for linear simple harmonic motion, we need a stable equilibrium, and we need one important condition, which is the restoring force. That is the force that acts on the mass when it is disturbed from the equilibrium position should be proportional to the displacement. Here, we start with x equal to 0 as the equilibrium position. If the position of the block is x, the displacement is x. In this case, right now, you can see the displacement is 12 centimeters. Or now, the displacement is minus 12 centimeters. And you get simple harmonic motion. Every simple harmonic motion that we are going to look at will be compared to the block and the spring. Well, let's get started with the math. So we have this spring with a spring constant k, newtons per meter, and we have a block of mass m, and the equilibrium position, we call it x equal to 0, and x is measured positive to the right. We also know that the force that the spring exerts when the position of the block is given by x is minus kx. Now, what do we want to do? We want to describe the oscillation. That means we want to be able to tell the position of the particle at every instant of time. In other words, our aim is to find this function, position of the particle or the block, as a function of time. If I know this function, then I can plug in any value of time. For example, t is equal to 2.67, and the function will give me the position x at that instant. So this function will give me the position of this block at every instant of time, and that is a complete description of the motion. In fact, if I want to know its velocity at some instant of time, I just have to differentiate this function, dx by dt. When I differentiate this function as a function of time, I'll get another function, which is the velocity as a function of time. Again, I can plug in any value of t to get the velocity at that instant. I can go ahead and differentiate this function again to get the second derivative, d2x by dt squared, and that will also be a function of time, which will give me the acceleration of this block at every instant of time. So you can see that if I know x as a function of time, we have a complete description of the motion. Now picture this. I pull the block by 1 centimeter and release it. I get x as a function of time. I pull it by 10 centimeters and release it. I get a different function, x as a function of time. Or I compress the spring, that is push the block to the left by 0.1 millimeters and release it. I will get an oscillation, which is a different function of time. So for each initial position, I'm going to get a function of time, a different function of time. So you can see that there are going to be an infinite number of functions, each corresponding to a different initial condition. Alternately, I might give it an impulse to the left and it starts oscillating. That's going to give me another function of time. Or I might give it an impulse to the right. So for each different starting condition, I am going to get a different description of the motion. So there are going to be an infinite number of functions x of t, each one describing a possible motion of the block, each corresponding to a different starting conditions. That's called initial conditions. Now, All these functions have something in common. That is, each one of them has to obey Newton's second law. Now, Newton's second law, F is equal to ma, is an instantaneous law. What does that mean? It means the force exerted on a particle at some instant of time will give us the acceleration at the same instant of time by this equation. So this equation holds instant to instant. It holds at every instant of time. In fact, all laws of physics are instantaneous laws. If x as a function of time is a possible motion, it has to satisfy this equation. So at some instant of time, when the position is x, the force is minus kx, and that should equal mass times acceleration at that instant, which is d2x by dt squared. So what we have here is an example of a differential equation. What is a differential equation? It's an equation containing derivatives. The highest derivative that this equation contains is the second derivative, so it's called a second order differential equation. Fancy words, no need to get worried about it. Let's write down this differential equation in a slightly different form, which is more transparent. The acceleration d2x by dt squared is equal to, bring m that side, minus k by m times x. Let's spend a few minutes looking at this equation. I'm going to take this equation to the next page. So what this differential equation is telling us is find a function x of t, which if I differentiate twice with respect to time, will give me back the same function except multiplied by a negative constant. Now we might guess, for example, let's take a guess. Okay, remember, systematic solving of differential equations is beyond the scope of this course, but let's get familiar with it. We might guess, for example, a sine omega t, where a is some constant and omega is some other constant. Why did we guess this? Because if I differentiate sine, I get cos. If I differentiate cos again, I get minus sine. So differentiating a sine function twice is going to give me negative of the sine function, which is what we want. Let's try it. If this is x, what is dx by dt? That's going to be, a remains as it is, derivative of sine omega t with respect to t. Now omega t is called the argument of the sine function. So first let me differentiate it with respect to the argument. That gives me cos omega t. I'm going to use the chain rule, multiplied by derivative of the argument with respect to t. That is, derivative of omega t with respect to t gives me omega. Let's differentiate this again. d2x by dt squared. That gives me omega a stays as it is. Differentiate cos omega t with respect to t gives me minus sine omega t. That's the derivative with respect to omega t. I want the derivative with respect to t. I have to multiply this by derivative of omega t with respect to t. That gives me another omega, so I get this. So check it out. This function x is equal to a sine omega t, when differentiated twice, gives me the same function back except multiplied by a negative constant, which is what we want. So if I choose omega squared to be equal to k by m, this is a perfectly good solution. So if x equal to a sine omega t, the second derivative is minus omega squared, which is k by m. So minus k by m x. So it satisfies this equation. I leave it as an exercise for you to verify that b cos omega t will also work. In fact, the sum of these two, a sine omega t plus b cos omega t, will also be a perfectly good solution. So how do I write the most general solution? Now here you have to take my word for it. Here is the most general solution. X as a function of time is a sine omega t plus phi. Here a, omega and phi are constants. Let's quickly verify this. The first derivative, dx by dt, is a cos omega t plus phi, where I have differentiated it with respect to the argument. The argument is the stuff in the brackets. Okay? but I want the derivative with respect to time. So by the chain rule, I have to multiply it by the derivative of the argument with respect to t, which is omega. Remember, phi is a constant. The second derivative by the same logic is going to be minus omega a sine omega t plus phi when I differentiate it with respect to the argument. And once again by the chain rule, I get another omega. So you got this. Now this is nothing but x. So if I compare this with our differential equation, omega squared should be chosen to be k by m, or omega should be taken as root k by m. So finally we have this result. The solution for our differential equation is this function where a, omega and phi are constants. But the moment you give me a spring and the block and this arrangement, I know omega. I know the spring constant. I know the mass. Omega is determined. A and phi will be determined in a different video from the initial conditions. Different values of A and different values of phi will give us different solutions corresponding to different initial conditions. I'm going to stop the video here, but one last comment. This omega will turn out to be proportional to the frequency of the oscillation. I'll describe that again in another video. So the next video is going to be an introduction to differential equations, mathematically very simple. I hope you will enjoy that. So goodbye for now until the next video.